Okay, thanks everybody for attending another one of the Siemens online webinars. Today we're going to be getting into part probing in auto mode, specifically using G-code. So I think you're going to find that it's some pretty good content. We got a lot of material to go through, so we're going to certainly get at it. I absolutely encourage people to certainly ask questions based on the topic. What we'll do is we will reserve a period at the end of the seminar to discuss those questions, but feel free to type them in as we go. In the Q&A panel would work best for me. This way you don't have to worry about kind of thinking of questions at the end. So if you see something pops up, type it in. You know, if we happen to end up covering it in the content later down the road, don't worry about it. It's not a big deal. All right. So with that being said, for those of you that know me, hello. Great to get a chance to talk to you again. For those of you that may be new to these webinars or haven't had a chance to meet me yet, my name is Chris Pollock. I am the Virtual Technical Application Center Manager. So basically that means that I am driving a lot of the web-based content, at least from the US perspective, specifically to operation and programming content. So I am a resource here available to any and all, end users, dealers, importers, OEMs. So if you have any questions, especially based on operation and programming of our Sinumerik portfolio, please feel free to reach out. I'd say the best way to get a hold of me is certainly my email address, but if you're in a bind, you can certainly always try to give me a call on my phone as well. So I did mention in the initial slide of those of you guys that were jumping on or just kind of waiting for the event to start, that we got a couple webinars coming up. We host these webinars every 6 weeks approximately. So coming up, we do have conversational programming and shop mill. We've been doing a lot of these webinars on pretty advanced content that I want to make sure that we still address some of the earlier or entry-level content. And then after that, we are going to get into a very advanced topic, which is programming a B-axis mixed technology lathe. So that would be a 5-axis lathe or more, depending on if it has a subspindle or not, that would have a full B-axis programmable or milling style spindle on it. So that's coming up in February. Hopefully you guys can attend. So keep in mind, all of this material, as well as a lot of other resources, can be found on our main website, which is the Siemens.com CNC4U website. The link is there on the top of the screen. And if you want to drive directly to the library of webinars or also see what next webinar is coming out, we promote these physically on our CNC webinars link. So that would be, it's accessible from the main page, or if you use the webinar link, you can drive right to it. Now, additionally, what you can find on our CNC4U page is our in-person workshops that we host out at our training facility, our TAC, Technical Application Facility, that we have out in Elk Grove Village, Illinois. So it's right by the O'Hare Airport, maybe 10 minutes away. So please feel free to check these classes out. There's no cost to come and attend the classes. They're 3 to 4 day workshops. And here, if you go to the CNC Operation and Programming section on the web page, you can see the classes, there's an agenda. You can even register right there online if you're interested in coming out and attending. We got some great material for you guys to take advantage of. I personally host the 5-axis class, or what we call our level 3 class, and we have some great instructors running some of the other content as well. So if you can make it, we encourage you to come out, join us, and take advantage of some of these classes that we're offering. Additionally, keep a lookout for some new classes we're developing. On the probing content or topic, we are going to actually host in-person measuring or probing classes as well. We hope to get that class launched this year. So keep your eyes out for that, as well as some other exciting new content or topics that are coming down. Okay, so we have 3 primary controls in our portfolio. Today's topic will be specific to the 828 and the 840. For those of us that are maybe using the 808, some of this will apply, but majority of this is tilted specifically to the 828 and the 840. So with that being said, what's the intention today? What are we going to try to actually get into and take a look at? Well, we're going to do in-process probing. So first, in the beginning, we want to talk about a little bit about the jog side, but what I really want to talk about is how do I set up a part probe, how do I calibrate a part probe, and then from there, we're going to go into how do I utilize a part probe in an automatic routine or during process run. A lot of guys use these things for setup, but they're not taking advantage of, well, maybe I want to adjust offsets in a part program as I'm running, or I want to come down and take some measurements. So we're going to take a look at those types of features. We're going to use the built-in cycles of the control, and then I'm going to show you some unique CNC commands that would allow you to completely write your own cycles. And then at the end, we're going to talk about some of the reporting structure that's built in that you can take advantage of within the control. So, the basic methods of measuring. So we can measure in both jog or in auto, and then obviously that can handle both tool and part probing. Now in this seminar, we're going to be specifically looking at the part probing side of the world, but the cycles that we're looking at, you'll see a lot of equivalent ones when it comes to tool probing as well. So you want to take a look to see what's available in the control from the tool probing side. So first, let's talk about the jog environment a little bit. So when it comes to jog, when it comes to the cycles available in the control, the 840, you get all of the cycles as standard function. So there's no option here. Really what it requires is just having the appropriate hardware to take advantage of them. Now when we get to the 828, we give you a reduced library of cycles, and you'll see in a couple slides which cycles you get out of the box on an 828. So if you want to have the full library of measuring cycles that you would get in an 840 in the jog environment, you do need the option we call extended operator functions, and that's our P16 option. So just be aware, maybe if you're bouncing between 828s and 840s and you're seeing a difference in availability of cycles, it's most likely because of this option. So you can add the option to have the same amount of functionality in an 828 as you have in an 840. So these cycles can be used certainly for tool measurement as well as workpiece measurement. And for us, we're going to start to look at them from the workpiece side of the world. Now, when we're using the cycles, what's pretty unique about our cycles, especially when you compare them to maybe some of the purpose-built cycle by the probing manufacturers, is our cycles don't actually require to have physical probes in the machine. So they're they're adaptive. We'll look to see what tool you have in the spindle. If we see there's an end mill or an edge finder in there, we know it's a manual tool. We still let you use the cycle in the jog environment. Now, auto is a different story. You obviously have to have a probe because it's all automatic processing. But if you need to set an edge, just check an orientation, maybe tip an angle because you're offsetting a skewed vise, and you don't have a part probe, you can still use the cycles that are available in jog in the Siemens Cinemerik controls. But for us, we're going to be looking at using the probes with a probe integrated to the machine. So there's two methods that you're going to use these cycles to do. You're going to measure, and then potentially you're going to start setting work offsets. So measuring would be if I just want to check features or dimensions on a part, or just get a rough idea of where different features are. And then certainly work offsets are going to write to whatever given offset I tell it to in its cycle. Now here is the full library of cycles that you get in jog. Again, on the 840, standard out of the box. So all the cycles you see here can support probes, but also could be used manual. Now the red ones, the highlighted red cycles, those are the standard cycles you would get on the 828. If you want to get all the cycles, then you're going to get that P16 option that I mentioned before. Okay, now in the nature of our cycles being very adaptive, you can even start to use what would be typically thought of as an advanced cycle for maybe a 5-axis machine or a machine that has rotaries. Well, the system has the ability of still utilizing these functionalities with or without the rotaries. So things like align edge, which allow me to pick 2 points and figure out where my part is skewed. Well, even if I don't have a physical rotary on the machine, I can write it to the coordinate system and let the machine spin the coordinate system to align itself to the part. So I always like to say that we allow the machine to kind of align to your process instead of forcing you to align your process to our machine or our control, our functionality. Same stands true with the align plane function. This function is very commonly used when setting up a 5-axis machine, but could still be used on a 3-axis machine, and even manually for that matter, if you had a surface that you need to square up to. Maybe you have a machine like a Bridgeport style machine where you can tip the head and you want to make that normal to some surface. You could probe a few points, figure out where that rotation is, and then just manually tip your head and move around in relation to that surface. So for us, the intention of this course, we want to start talking about creating physical probes, automatic probes, 3D probes. How do I build them? How do I calibrate them? And then how do we use them in auto mode? So in the jog environment, first step would be to certainly create yourself a part probe. And the way you're going to do that is you're going to go to the offset table or our parameters table. You're going to go to your tool list like you were building any other tool. But under selecting new, you're either going to pick the 3D probe that's available under the favorites column, or you're going to go to our special tools button. In there, you're going to see all the different probes we support. So we support a large variety of probes. Your standard probe, your standard 3-dimensional probe would be the 710, the type 710 probe that we see on the right side of the screen that's highlighted. But we also support mono probes. Those are probes that only have limited measuring in certain directions. We support L probes or star probes. So maybe you need to drop into a bore or you want to measure up underneath something. So those are all the different configurations of probes. You can actually commission up to 10 different part probes on a Siemens control and allow that to certainly communicate to a singular input device if you need it to. So what you'll do, you'll pick your probe. In this case, we'll pick a 710 or a 3D probe, and we'll create that part probe. So now this way, when we physically insert it into the spindle by doing a tool change, the machine knows, hey, all of my cycles can be used in an automatic method because you just told me we have a probe in the spindle. So that's kind of what the trigger is. Now, a lot of guys overlook this step when starting to use part probes. And that's, I want to make sure that the Ruby or my stylus is running concentric to my spindle. Now, all these are adjustable on all these different manufacturers of probes, usually a couple set screws, but you do want to make sure that you spin the spindle, you indicate in, and you get it as close as possible. The cycles are certainly set up to compensate for any run out, but why add error where we don't need to? That's always been kind of my rule of thought. So get it close. The cycle will compensate for any inaccuracy that might be there. You know, you're never going to get this stuff perfect, but you certainly don't want a probe that's got 10th out run out in it. So just remember to do this step first before we go any further, because you don't want to calibrate with a probe that's out and then adjust the probe, because you'd have to recalibrate then. Now, what do I mean when I say calibrate? Well, we have to know where this probe is in space, and we have to then measure it against some known values, known positions. So there's two things you got to calibrate. You got to calibrate the length and the diameter. So the diameter is really calculating and compensating for any run out within the probe, as well as any inaccuracy in the stylus diameter. You know, you're going to tell it the diameter when you built that tool, but nothing's ever perfect. So first step and the easiest of the two processes is really actually compensating for the diameter, calibrating the diameter. So in this case, you're simply going to have a known diameter. Typically, you're going to purchase what we call a ring gauge. It's really just a standard that has a known ID dimension that's ground in. A lot of times they're 2 inches, but they can be any size. It really doesn't matter. You're going to manually place the probe somewhere in the middle of this ring gauge. Now, the ring gauge has to be mounted to the machine. It can't have the potential of moving. Obviously, we're going to start to move around and touch a couple sides, so we don't just want it sitting there. You could use a strap clamp to hold it down to the table. Sometimes we butt them up against a mag base. There's not a lot of pressure on these switches. Probably there's more force induced by the table moving around than anything else. So you just want to make sure the ring gauge is sitting fixed on the table. Again, with the probe sitting roughly in the middle of the ring gauge, you're going to tell it the diameter that the ring gauge has been machined to. Then you're going to hit cycle start. And the machine is going to go and automatically measure all 4 quadrants of the inside of this ring gauge and calibrate its probe. And it's writing to a bunch of back-end parameters automatically for you here. So like I said, this is pretty much the easiest of the calibration steps. The next step, which gets a little trickier, is calibrating the length. And the reason why I find it gets a little trickier is because there's really two different standards of how you set up a machine tool when it comes to tool length compensation. We have what's called positive tool length compensation. That's where my physical tool length in my tool table would actually be a positive value. And that would be a value of the tool from the tool tip measured back to a gauge line dimension. Generally, it's the face of the spindle or somewhere close to that. So that's what we refer to as the positive tool length method. Now, on a lot of lower technology machines, 3 and 4 axis machines, it was always common to set negative tool lengths. So I wouldn't worry about setting any work offsets. I'd just bring my tool down to the top of my part and then measure my tool. And I'd get this large negative value because it's the distance from the machine home to the top of the part. When calibrating probes, we have to take both strategies into account. So you don't have to calibrate it twice, but you have to calibrate it to match how you have your machine set up. So I would say the positive tool length method, certainly when you get to the 5-axis world, this is pretty much a prerequisite. You know, there's a few different kinematic types that could be run with negative tool length offsets, but it's very limited. And typically, once you get to any type of rotating spindle machine, whether it's a mixed kinematic or a head-head kinematic, you have to use positive tool length offsets. The machine won't run otherwise. So we as a control manufacturer, we tell people right off the bat, if you're running 5-axis or greater technology, you have to run positive tool length offsets. So with that being said, you're going to need to calibrate your part probe for positive tool offsets. So what you're going to do, and we're not going to go through this procedure in huge detail. Certainly, if you guys have to get into calibrating any probes and you'd like to get this procedure, shoot me an email. I'd be happy to share the slide deck with you or give you the specific procedure. But the basics of how you would calibrate it is first, you're going to give the machine a rough tool length of the tool probe. So here it would be a distance from gauge line to tool tip. You can do it with a tape measure. You can come down to a piece of paper, just get a rough dimension. You want to have that dimension in initially. As well, you would have put the diameter in and probably already run it through the diameter calibration. Now, you got to calibrate relative to a fixed datum. So generally, I use the table surface if I can get to it as my fixed datum. So without the tool and the spindle, you want to set the work coordinate system. So if I was to bring the spindle all the way down and touch that table, the display would be reading 0. So I would get a large negative offset in my modal or loaded work coordinate. So now what you do is you physically tool change the probe in. You move it down and you get it close to the table surface. There's a machine parameter I'm referencing here in the procedure. You do have to be within it. I would say on average, be within a ½ an inch or so of the surface. And then what you're going to do is you're going to initiate a cycle start while you're in the calibration length function. That's going to make the machine move down. It's going to touch that surface. And what you're going to see is you're going to see an updated tool length going to the tool table. That's validation to you that the tool is calibrated. Now we know exactly what the true length is. It's possible to measure these tools off a laser presetter, but not with a touch presetter because you don't know which switch is switching. So you typically want to go through this process when calibrating your part probe. Now the negative, this is just going to be a little bit different. Here, you would not have any value in your work coordinate system. You would come down, take a rough measurement to the top of the table surface. That would get entered in as your tool length offset for your Z. You'd go to the calibrate length field, set the Z field to 0 again like before, and now cycle start. Let the machine come down and measure that table surface, and you'll see that it'll update a large negative offset into your tool length offset. Now all your dimensions would be relative to table surface. You would want all your tools to be relative to table surface, and then you could just put small shifts in the work coordinate to the top of the part when it's time to cut apart. Okay, so a lot of the steps I talked about and furthermore, the functions we're going to get into here in a second in using our cycles can all be found in this measuring cycles manual. So this is kind of like our Bible when it comes to the measuring cycle functions. So you're going to want to do yourself a favor and you're going to want to download this PDF. So to find this PDF as well as a lot of other PDFs we have, you're going to want to go to our support.industry.siemens.com website. Now, there's a ton of stuff there. Siemens is a huge company, and it's not just the CNC environment that's going to be found here. All sorts of PLC products, General Motion products can be found here. So what you want to do is you want to search for the name of the manual. In our case, it's called Measuring Cycles. From there, it's going to show you the results. You're going to see probably right up at the top, first one is going to show you this Measuring Cycle manual. There may be some older dates, so I always suggest picking the latest one that you see, or the highest one on the list, to tell you the date it was published. Download that. It's PDF, totally free of charge, not locked out. Anybody can get them. And this is where you can start to find a lot of the reference material for the content we're covering today. Okay, so now that we kind of talked at a high level of jog and discussed how to set up a probe, now it comes down to, well, what can I do with my probe when I get to automatic mode, when I want to start utilizing this probe? So, first thing we have to discuss is that the probing cycles in auto are an option, and they are an option for both the 828 as well as the 840 control. Now, does that mean that they're not in your machine? Not necessarily. It's really up to the OEM when they build that machine as to whether or not they want to equip that option. So you may find, especially in the 5-axis machines, a lot of these are already coming right out of the factories with the measuring cycles. But you do need to have this license to be able to take advantage of them. License is very reasonably cost, and it's an easy thing to add. There's no extra setup steps involved aside from just really registering your internal CF card to us that you have this license available and turning on a checkbox, and they'll be on. So if you don't have them and you want to add them, pretty painless. You can give us a call, we can quote it, or you can go right to your OEM. I'm sure they'd be happy to quote it for you, and you can add in the features. So the license option is the part number you see down here towards the bottom, the 6FC number. We generally refer to it as a P28. That's right there in the middle of the part number, that P28. But when you call, if you are interested in getting it, I would say you want to have the entire license number, the 6FC 5800 number available. And then from there we can quote it for you. Okay, so these cycles that we're looking at now, they really came out in what we call version 2.7 software, and that's in our latest Operate interface. Now, we've had plenty of interfaces prior to this, and they had measuring cycles available for them, but if you're familiar with the older cycles, you're going to find these are much easier to use, much more user-friendly. Before, you used to have to set up a lot of discrete variables prior to the cycle, all in G code. There was no graphics or animated elements like you see here to kind of tell you what the cycle needs. So all that stuff came live in 2.7. So as long as you have an Operate system and your software version is 2.7 or newer, which if you have Operate, I can almost guarantee it will be, then the cycles that you're going to see here are fully available for you. Okay, so the cycles can be supported in both a shop mill or a conversational programming environment, as well as our program guide, which is our G code. This session, we're going to specifically look at just the G code side of the control. In the future, we'll probably come back and revisit this seminar. We're looking at it specifically from the shop mill side. So what can we do with them in auto? What are the most typical functions that you're going to find people are going to use these for? Certainly work offset correction. So whether I'm afraid that the part gets loaded, slightly skewed, I want to come down and align to it. You can use it for adjusting tool geometry. So just because you're measuring the part doesn't mean you have to write the correction into the work offset. We could write it into the tool offset. You know, maybe I'm coming down in a pocket. I'm expecting that end mill had machined the pocket a ½ inch deep, and it's, you know, a couple thou shy of that. We can write that correction to a tool offset as well as have tried to shift the work offset. Or you can use it for measuring functions. And typically measuring would be for reporting purposes or tolerancing errors, right? So when I go to measure, we have some options that you'll see where we can either flag it that it's out of tolerance, or we can just create a report for you if you want to be able to catch and have traceable data. And then certainly you can use it for measuring tools as well. So this is the library of cycles that are available for you with that P28 option. And this is the functions that we're going to start to look at. So you're going to see a lot of common cycles to what you're probably already used to in the jog environment. A few unique cycles here, as well as probably a couple cycles that we saw we recognize are common from the setup side, but not typically used over in the programming side. The other thing that this differs a little bit. In jog, you're just going to run that one cycle, where here I may actually combine a couple cycles. So maybe I need to do an alignment off a couple bores. Well, instead of having one cycle that allows you to do it full cycle, you can use the two whole cycles in conjunction with each other, and then do some math, write some variables, record some data. So that's where this stuff gets very, very flexible and very powerful for you. So this is an example of the first part we're going to look at and see how it's methodized. So here, just keep it very simple. I just want to be able to come down to a block that's staged on my workpiece surface. I want to find the top of it, so I'm adjusting for any maybe inaccuracy during the loading process. And then I want to find the center of the block. So the program you see here would be how I would see this program methodized in G-code. And the cycle 978 and 977 are the two cycles that are going to handle this process. Now, when I get to the cycles, first step is knowing where to look for these measuring cycles. So when you start a G-code program, you're going to want to obviously create a new program, go into G-code, and then you're going to want to expand the horizontal keys over by using the gray right arrow button. Sometimes that's a soft key on your touch screen. A lot of times it's a hard button that's usually next to or towards the lower right-hand corner of the screen. That'll expand your horizontal keys over. So when you expand them, you're now going to see a measure workpiece or a measure tool button. And for us, we want to do an edge measurement, in the first case of a Z. So we're going to go to the edge distance button. You're going to see a bunch of options of vertical soft keys come up for different cycles. And we're going to pick this top cycle right here, which would be an edge kick. And the edge kick, or the edge measure, will allow me to then do a measurement in any number of my three linear axes. So once you come in, you select that cycle, then you're going to see where it's going to pop up this little conversational interface screen. So from the cycles perspective, it's pretty straightforward. First question we're asking you is, what are you doing? What's your intention? Are you setting a work offset? Are we just doing a measurement? And then I might have to pull the data out of variable, or am I writing to the tool offset? So in my case, I wanted to write to the work offset. Then I need to select which offset I'm writing to. Now this doesn't have to be the offset that you're currently running. I may want to write to a completely unique offset because I want to just do a compare between the two. So don't think this is the offset you're running during the part program. It's just where you're writing to. Now you have a couple options of how you want to write. So you can write to the coarse field or the fine field of the offset. So we're going to go in, you're going to look at the offset table. You can see how we have two different areas that we can use on work offsets. Fine is kind of like an incremental adjustment. It will add into the coarse field. So if I'm doing a modification of a coordinate, a lot of times I like to write to fine because maybe my original coarse one's still valid. And again, we're just picking up some inaccuracy in maybe the loading process. So why have to delete that offset every time? If I know that the first one is just a rough offset to get me close, then I might want to write over the coarse. So that's just a matter of selecting the coarse or fine field. Next step, you have to define your direction. Now, you notice nothing in this cycle has any X, Y, Z coordinate positioning. So it's up to you, and if you look at the program here on the left, you see I have a little rapid move to just a safe position prior to my measure. So it is up to you to pre-position the part probe to get into location. Now I tell it which axis I want to move, in our case Z, the direction I want to move in, and then where do I want to go. So these last three variables, this is telling it where we're measuring to. In my case, I'm measuring to Z0, or the top of my part. How close do I want to get to my Z0 or my Z location? This doesn't have to be 0, mind you. If I'm down in a pocket, it could be -1/2 inch. But how close do I want to get there before I start slowing down the feed rate to a measuring feed rate speed? So in our example, I was sitting 1 inch away. So that means it's going to come down to 1/2 inch, because this is 1/2 inch off of Z. This is an incremental value. And then I'm going to start feeding. And then I'm going to trigger. And once I trigger, I'm then going to look at my safety distance, my TSA field. And this is really a tolerance. So it's saying, hey, I need to make sure that I'm within, in this case 20 thou, of what I measured, or I'm going to error out tell the operator that there was an issue. Sometimes I see guys that they're not worried about erroring, they just wanted to set an offset, so you'll put a very large value in TSA. That's okay. This is just a tolerance value. Then from there, we're going to do the next measurement, which is coming down and finding the center of the part. So if I go to the spigot button, that was right next to the edge distance button, I now have a couple options here. I can work around a rectangle, I can work around a boss, I can go around a boss that maybe has a flat or a feature in the way, so I'm just hitting 3 points. So in our case, we're going to pick the first upper soft key, which is measuring around a rectangle. And from there, we're going to see a similar type of screen. So same kind of questions. Where am I writing to? What's my task? What offset are we writing to? How do I want to write? Then you get a couple extra pieces of information here when you get to this cycle. We need to know the length and the width of the feature you're measuring. So this way, because this one's going to do a bunch of positions, right? I'm going to have pre-positioned it roughly in the center of the feature. So if you look here in the part program, we got a little rapid move just prior to 977. And then it's going to automatically measure 4 sides. So it's going to go this distance plus a parameter that's been preset that will give kind of like an overrun distance. I can give it an angular offset if I know the feature is tipped at a big angle. And then I'm going to give it my DZ, which is my search distance down. So this will depend on where I was sitting. So normally I want to make sure that I'm coming down far enough in the edge. So this again is an incremental move, but this is a physical position move in the Z-axis to come down and do its measurement. You can enable a protection zone in case you're worried about it going out too far and hitting something. And then I have my feed, my incremental feed offset, just like we had before, as well as my tolerance. So from there, that's going to allow us to get a part program, and she's going to come down and measure these features. So we're going to jump over to Sinutrain, and Sinutrain is a machine tools simulator software that we like to use, and kind of show you what's going on here. So first things first, I'm going to look at my work offset table, and maybe or maybe I don't have some offsets in my find. So I'm going to zero these out. So I'm expecting these offsets that are seeing in the course adjustment, this is my course field, that would have been preset, right, when I first set up the job. So now we're going to go and we're going to take a look at our part program. So we're going to look at example 1. So what does example 1 do? So the header stuff is pretty typical. Now, I happen to be running this on a 5-axis machine, so I'm using my swivel cycle to send me to a clear spot and make sure my table is square. Cycling header wouldn't be required if you were just on a 3- or 4-axis machine. Then I'm setting up the workpiece just to have some graphics so we can see. Then it's a matter of tool changing to the appropriate probe that I want to use, setting up some feed rate, pre-positioning my part, and now come in and activate the cycle. So like I mentioned before, to get to the cycles, you want to find your gray arrow key to the right. You're going to hit it, and you're going to expand the soft keys. Prior to getting this option, you most likely don't have any other soft keys here, so this gray button wouldn't even be there. So that's another good indicator. If you don't see the gray button, that means you don't have that licensed option. You click the gray button, you pick it, and then we're going to come down, pick the appropriate cycle, just like we showed. So in our case, here's our cycle. Now I adjusted this one just a little bit, but here we're measuring in the work coordinate, G54, and we're writing to the fine offset. So we're doing that for both the Z measurement, and then when we walk around the boss, same dimension we just talked about. Now, if you want to see what the protection zone looks like, this would be a case where I could then give it some safety areas. I'm not too worried in my case. And then we can write that again. And again, you notice I'm writing to the fine as opposed to the course field. So when it comes to running it, if we just go into auto mode, I'm going to run a cycle start. Now remember, my offset currently is at 0. So as I'm running, machine's coming around, positions, does its measurements. I go back to my offset table, and now I see it filled in some correction values. Now we're in Sinutrain, so we're emulating an actual switch. Reality is I would expect these values probably to be a lot closer. This is just the beauty of simulation and graphics. But what is nice in Sinutrain, a lot of people don't realize, is you can actually run probing cycles. But you do have to calibrate the probe prior to being able to run any of this stuff in Sinutrain, or have had a machine that has been calibrated. Okay, so back to what we're doing. So basically, just like we saw, here we're coming down, taking a measurement in Z, walking around our surface, going to a safety retract, and that is what's physically going in, writing these offsets. Here it did a little bit of an update, and moving on. So the flying keeps me from wiping out these first offsets. That's also handy maybe if I'm doing adjustments over the day because I'm getting some thermal expansion. But I know when I come in the next day and the machine's cooled down, I can just zero out the flying because I'm going to be a lot closer than I would be at the end of a work day. Okay, so with that being said, let us transition back to our slides and take a look at how we can start building off of these functions. So the next example I wanted to show you would be, well, what if we want to compensate because our part is tipped at some kind of an angle? What if it's not straight? Or in this case, I just machined a little boss, and I want to measure the skew. So I can use the align edge function, and the align edge function will then allow me to take measurements off an edge that's not necessarily parallel to the machine coordinate system. What's cool about this is once I align the edge and I activate that work offset, then my other measuring routines will now move relative to the new adjusted coordinate system. So align edge can be found under the edge distance field, but now we're going to use the one that shows the box at an angle with the two little arrows, and that is going to get us into this align edge, or this cycle 998. So there's a couple new fields when you get to align edge. First thing, the angle correction field, your coordinate rotation field right here. You want to pick how you want to apply the offset adjustment. So am I writing to a coordinate rotation, and I'll show you where that is in a minute, or am I writing right to the direct axis of my rotary? This machine happens to be a BC machine, so it's got a rotary around the Y and a rotary around the Z. You could have an AC machine. If it's a 5-axis machine, you'd see this reflected here. Generally, I like to always write to my coordinate rotations if I can. Then I can control how I want my measurements to kind of compensate. We got this para-axial or parallel to edge. So in our case, I wanted to run parallel to the edge because I have a part that's tipped 20 degrees. So I told it that. Then you're going to tell it what the measuring direction is and an axis, as well as the positioning axis. So that means I'm physically moving the probe in the Y to take the measurement, but then when I got to move over, in this case to the right, to the next move, that's going to be my positioning axis right here. That is basically everything else that we filled out. It's pretty much the same. I have some search distance parameter. That's your L. That's how far you want to maybe allow the machine to move during the measurement. If you have it tipped at a known angle, you can give it that. In my case, I did. There is a protection zone option under this one. From there, that allows me to start to align and do some corrections. And then really the other cycles in this program were just the same cycles we used already. So let's take a look and see what this program really looks like in some detail. Okay, so I have an example 2 methodized for us. Same header stuff, but in my case, I'm going to just machine a boss, and I'm machining a boss that's tipped at a 20-degree angle. So this way I had something to align to. So when I'm all said and done, I'm going to actually write a new coordinate system that's aligned to this tip. So it thinks X is actually moving up and down at an angle. Then I load up my probe, I come down, and just like before, I have to go into a set position. Now, I happened to pre-orient the spindle with an S-pause. That's something we'll get into in a little bit under the mesh cycle. Here, the cycles automatically handle the spindle orientation, so you really don't have to worry about it in the part program. But I do have to pre-measure or pre-position to a location I want to take the measurement from. And then I'm going to, again, expand, go to my measure workpiece, find my edge distance in this case, and my skew. And that's what's going to drive me into this cycle. From there, I fill out my fields. So I'm going to tell it where I want to write to. So here we're writing to our G510 work coordinate. And what that's going to do is that's going to basically do 2 points and calculate what this true edge is. Is it really 20 degrees or is it something off a little bit? From there, we're then just going to come down and do the same measurements you just saw, but I'm now going to write to the fine offset. So I'm going to then adjust to my fine location as opposed to where I was originally. Now when I did the first machining, I'm machining at G54. Right, so I machine the part at G54 and then I measure into 510. So the G54 doesn't get adjusted or changed in this scenario. You can use the same work coordinate if you wanted to. So what is the result going to look like? So let's look at it in a few stages. If you notice, I put a couple stop points for us with some optional stops. So first thing I want to do is come down and align an edge and show you where that writes to. Okay. So if we go to execute, we turn on our op stop command, and I'm going to go to 510, and I'm going to zero it all out. I don't want any values in my 510 at this point, because I want you to really kind of see what's happening now, and when does it happen, which is important. Okay, so we're back here in auto. Let me jump over to the auto screen, and we're going to run with my single block, or my optional stop on. So she's going to machine the feature, and it's going to come down. So right now it's machining the boss, walked around. Now we align the edge, and we did an optional stop. So let's see what we see in the offset table. Now it hasn't gone around and hasn't tried to measure around the feature, just align the edge. So what did the system do here? Well, it knew that I was just taking a measurement of a rotary value offset, but it also automatically copied whatever values are sitting in the work coordinate system, and even the fine values for me. So it knows enough to say, hey, well, if you're going to do even something simple like an align edge, you're probably going to want those values down there. Now, you're probably going to update them at some point, which we do in a second here, but it copied them for me, even though I never measured anything in the X, Y, or Z. Now, what it did do in the measurement is if on any work offset you go to details, you can see what we call coordinate rotations. So this would be similar to like trying to adjust an offset in the direct axis, a C or a B, but this is just rotating about a linear axis. So this is saying that my coordinate system has to rotate about my Z positive 19.998 degrees off of that 2-point measurement. So that value is what the cycle really is doing. That's the true measured value. Had I not used coordinate rotation field, it would have wrote to one of these two direct axes, whichever one I wanted to tell it. I would have had to use C in this example. Okay, so we're here. Now we're going to cycle start. Machine is going to come around, and it's going to measure my Z-axis. So now if I look at my fine value, I now have a 338 as opposed to originally I had 230. So now if I looked at the cycle, I'm just adjusting the fine of G510, so it's only going to update that one field. And when I do one more measurement, it's moving around the X and Y, and then it updates my fine fields. So now I've aligned and reset all my XYZ locations, so I truly know where that part is. Okay. And again, that's just handled really through the cycle 998 to handle the alignment, and then come on down, and we've done the same process that we did before. We do a 978, which is just a quick little Z edge kick. I write to the fine. I just changed the work offset and adjusted my numbers a little bit. And same thing here. I'm coming around the spigot, measuring 4 sides, and writing it to the fine of G510. And now we're aligned to that feature. So now X, any movement I do in X at this point while that work coordinate's modal, because of the coordinate rotation, is going to move relative to that measured edge, not relative to the machine coordinate, because I've just rotated everything. Okay. So the next step in this process of measuring cycles is, well, how does it work when I get to 5-axis machines and I don't have the luxury of taking a measurement in my G17 or my base orientation? Well, that's what's really great about our dynamic fixture offsets, or cycle 800. I can take measurements in any orientation, and since it knows the rotary orientation, because it's dynamically tracking, it's going to derive the same value. So in this little example, I just set a work coordinate from the top and then swing her 90 degrees and set both those same two axes, my X and my Y. But I'm now tipped around. You know, maybe you got a case where you can't take the measurement from the top. There's something obstructing you. You got to tip it from the side. Or you got one of those compound wrap devices and you want to measure relative to that. You can do that, and it's going to write the appropriate offset as if it was sitting in G17. So we're going to take a look at the source program and then see kind of what it's doing to the offset table when it's all said and done, and how it's deriving the same numbers. So back over to our Sinutrain, example 3 is what allows me to take this measurement. Now in this case, since this is a 5-axis machine, it is mandatory for me to use cycle 800 to move things around. That's how our dynamic fixture offsets work. If you were just positioning this through direct axis moves without using either Traore, which is a 5-axis toolpath, or cycle 800, then what I'm showing you right now would not work. So you do have to drive things. So in this case, my part is sitting with the rotary table sitting at 0, 0. And I'm just going to come down. And in my case, I'm doing a simple. I'm not doing all 4 edges in one cycle because I had to break them up later anyway. So I'm just taking a measurement with the singular measurement. This is also a lot of times used for webs or veins or ribs that I want to measure. But in my case, I'm writing, and I'm writing to the course offset of a G511. So we're going to be working in 511 and 512 now. From there, I'm just going to take a measurement in X. I give it a rough dimension of my width, my web distance, or my rib thickness. If it's tipped, how far down do I move? And all the other parameters are really the same as you've been seeing. Then I'm going to do a measurement in Y. So we're going to take that measurement, and then we're going to stop. So we're going to take it, we're going to stop with an op stop. Then I'm going to use cycle 800 to basically swivel or tip my rotary 90 degrees up about the y-axis. So that would give me a b-axis rotation of 90 degrees. But the cycle is running as if I was straight up and down. So I'm then going to tell it to take a measurement. So I'm taking a y measurement, and then I'm going to come down, use cycle 800 again, right here, and then I'm going to take an x measurement. And if everything works properly, the machine's going to come up really with the same solution between the two, minus any inaccuracy in this probe trigger that we're simulating. And then I'm going to send it back up so everything goes straight. So if we look at the program, and we watch it, just so you can kind of see and get your head around what's happening, I'm going to come down, and let me rerun it for 1 second, because I was switching offsets. Sometimes the graphics in Sinutrain need a second to reorient. See, the path is correct. I'll watch. And then it moves the block to the right spot. Okay, so that is our first measurement that's coming around the top. So what that's doing is that's writing to 511, right? So that's coming up with these 3 numbers. And then we're going to continue, and we're going to do the measurement around the 2 sides. So around the first side, around the second side. That writes to 512. So then it's going to update right here. So I can zero these out, and we can rerun it. So she's coming around measuring the top. You see I got some slight change. The Z is not going to change, mind you, because I didn't take any measurements of Z. I'm just doing X and Y. Now we're going to swivel up 90 degrees, and she's going to take a measurement in Y. And there it auto-copied because it knew it must need it. And then it took the measurement in Y, took the measurement in X. I get a slight difference. That's, of course, with our simulated trigger. But I'm getting the same value as if I was standing straight up and down because of the dynamic fixture offsets. So you can absolutely probe at any orientation. Just use cycle 800 in conjunction with it. Okay. So we've been talking about the cycles quite a bit. But what I do also want to start to show you is you're not limited to just these cycles. So there are some native commands, some CNC commands that really drive these cycles. And specifically, we're talking about what we call the MEAS command. And the command syntax is actually MEAS, like the word measure. There are some variations of it. You got MEAS, MEAS-W, MEAS-C, and each have a little unique function. I would say the most common you're going to use is this MEAS-S, but this is the function that's actually running in the back end inside these cycles. This is what makes it all work. So what I wanted to do is kind of just show you quickly kind of how you can start to create your own cycles. Now, what's interesting about the MEAS command is since you're not using cycles, it doesn't require the license. So in theory, because the license is giving you our pre-methodized CAN cycles, the command is always in the control at all times. So when you want to look for information on the MEAS command, that's not going to be found in the measuring cycles manual because that's specific to cycles, but it's going to be found in this job planning manual. So you certainly want to go to the same source, but now you want to do a search for job planning. Download this manual. This is a great manual. This is my go-to whenever I'm looking for any weird or obscure functions in the Siemens world. I would say this one, and if you want, do a search for a manual we call Fundamentals. The Fundamental manual is, it's kind of equal. I'm jumping to one or the other. I would say Fundamentals is a little bit more standard functionality, and then job planning gets into all sorts of crazy stuff. Like nibbling and grinding and punching, and as well as a lot of obscure commands like the MEAS command. Okay, so how does it work? So basically from a syntax side, you're going to pre-position the probe into a location. Then you're going to give it a command called MEAS, M-E-A-S. Then we need to tell it a couple things about where we're going and what we're doing. So the MEAS command, first, inside its first variable, I need to tell it which probe I'm going to physically be looking to see a trigger of. So the system from an input side can support two probes. It can support an input from a part probe, and then most likely the second one's going to be used for your tool probe. Now, it's going to be up to you to know where each one was wired to, so that's critical. So, you know, if you're going to want to start to get into this stuff and you didn't install the probes, you're going to want to certainly talk to whoever did and find out, for one, which of the two inputs the part probe is going into, one or two. And then you need to know if it was set up for what's called a rising edge or a falling edge. That means, is the input high or low, and I'm expecting it to go to what state during the measurement command. And I don't want to say they're usually one or the other because guys can set them up any way they want. So in my case, my part probe is plugged into input 1, and it's set up for a rising edge. So I need to give it a value of 1 in the MEAS command. Now I'm just going to tell it to feed to a position. And you need to feed a little bit further than the edge you're expecting to trigger to. And all this does is this just sends the machine moving in a direction, and it will stop when one of two things happens. Either it sees the input, or it gets to the end position where I was trying to go, and I never hit anything. And then it'll just keep moving on with the program. It's a very kind of dumb, simple cycle, but it's the meat of what makes all of these advanced cycles possible. So from there, this is the program that I kind of put together, and I wanted you guys to start to see how we could methodize and what's a couple things we could do in trying to use the MEAS command. So you do have to know and handle a few other functions that would normally get set up by the measuring cycles. One, you're going to have to turn the probe on. So you're either going to have a machine with an M code that was associated to probe turn on and off, and then you're going to want to know what those M codes are. Machine I'm on happens to be M27. Or you might have to trigger our custom edge cycle. That's another way to turn things on. So this is certainly an area where you have to, you have to play around with how your machine is specifically set up. Then you're going to have to handle orienting of the probe. So generally, whenever you're taking measurements, especially if you're bouncing around different features, you're going to want to make sure you're touching the same point of the probe at each time. So you're going to want to position. So the easiest way to position a spindle is with what we call our S-pos statement, spindle position. And it's a matter of just saying S-pos equals and then an angular value. In our case, I want to go to 0. And then later, you're going to see that when I go take the measurement on the other side of the block, I'm going to do an S-pos of 180. So we measure on 2 points. So why don't we jump over and show you first what the program looks like, and then we'll dissect it a little bit more. So inside, we have a program, the program we were just looking at. And what it's going to do is if I'm going to run it, I'm going to just come over to a block. We're going to feed down, take a measurement of one edge. Then I'm going to jump over, take a measurement of the other edge. And then I'm going to do a little calculation here based on my two measurements to then position the machine to the center of this block. And these locations could be kind of anywhere. So that's the mechanism of the program you're about to see. So if I look back at the program, do my initial header stuff, load my tool, set up feeds, orient my spindle. Now this is a little redundant, I did it twice. Doesn't really make much of a difference here. I'm going to pre-position to a safe location. So in my case, I'm positioning to the left side of the block. My part, I'm saying that the block is 0, 0 on the left, and it's 6 by 6. So just so you get some dimensions of your block. So once I'm close, I want to turn my probe on, make sure my spindle's maintaining orientation. So I usually put the spindle orientation after the probe on. It can be in either spot. I put a quick M0 or M01 just to give us a chance to stop. Then I'm going to feed down and initiate the measure command. So this is the meat right here. Right? So I'm telling it measure equals 1. So that's probe number 1. And since it's a positive value, I'm looking for the rising edge. Now, if you don't know rising or falling and they can't tell you, if you pick the wrong one, the machine won't move. So it'll immediately think it kicked. So that's your trigger. And you can do this in MDI. You can type in measure equals and -1 and tell it to go to X such and such. And if it doesn't move at all and it just thinks it's done, then try the other one, try -1. Certainly, if she starts moving and maybe you manually trigger the probe and it just keeps on moving, well, you might be looking at input 2. So that's usually what I do. If I don't know anything about the probe, I'll just start it moving in air, and I'll just trigger it with my finger, assuming I'm allowed to get into the machine while it's in motion. It's a little trickier these days. And then if it stops, great. I know I'm looking at the right probe. If it doesn't, I'll just switch my number to number 2. And then I tell it where to go to. So remember, the edge of my part is 0. I'm telling it to go into the part a little bit, but I'm expecting it to hit at 0. Now, the one thing that a lot of guys overlook when they use this command, they're expecting some fancy, hey, I'm going to write to some variable. This doesn't do any of that. This literally just says move until you hit a point and then go to the next line. So it's up to you to then decide, well, what are you doing with this point at which you temporarily stopped at? So in my case, I'm using some system variables to do a couple things. I'm saying, hey, I want to set an R variable, and that R variable is going to take the current position of my x-axis in my work coordinate system. So that's what this $AA_IW. IW refers to work coordinate system. IM, I could substitute an M for the W, and that would be my machine coordinate system. So that's just saying, hey, once I stopped at that edge, pick whatever the current location is. And since I know I'm actually off of it by the radius of the active tool, I want to then also add the radius of the physical tool to this number, set it to R24. Then we're going to jump over, move a couple little position moves, orient my spindle. Oops, don't want to do that. Orient my spindle now to the other side because I'm now jumped onto the other side of the block, right? And I want to come down and I want to do a measure, and now I'm going in the opposite direction. So I'm sitting at 6.5, I'm moving to 5.9, and I'm going to do the same kind of logic to a new R variable. But in this case, I'm going to say, okay, well, I want you to subtract the radius because I'm on the other side to get the true edge. So you've got to think a little bit about where you're trying to go here. Then we come down. We do a little moving. Sometimes you might want to give yourself a stop read. This disables our look ahead temporarily until the machine gets past there. Sometimes the look ahead's too far and it may actually catch a value further down that I didn't want. So sometimes when you get to these measuring stuff, it's handy to use stop read commands. But I'm going to position up to a safe point. I shut my probe off because I don't need it anymore. And then I write an R variable, R26, and I just do a little math. I'm saying, hey, take whatever you wrote to R25, subtract R24 from it. What is that result? Well, that's the width of the block. Now I want to cut that in half. But I can't move to that value because who knows that R24 is 0? It may not be. So then I'm just adding whatever R24 was to this result, and that gives me the true center position of the block. Now to get there, a lot of guys don't know you can do this. It's pretty cool. If I want a position based on an R variable, system variable, whatever, you can literally type x equals R26 with a G0 or G1 or whatever, and she'll then move to whatever that location is. So if we look at the program here, and we look at our offsets, and we look at our user variables, right? I'm using 24, 25, 26. So we run the program and take our first measurement, and there we go. So it just came up. So in this case, based on where things fell and where it wants to trigger that switch, it thinks that I'm 200 thou past 0. Now I come over and I go grab the measurement on the other side of the block. So she moves over, takes my measurement. I think I went one more cycle stop in there. Oh, so I came over, took that measurement, and then we did a little bit of math, figuring out what that center position would be. And then I just drove that value in there. So you can start to get pretty creative using this mesh command. And again, this is the core function. So like if, for argument's sake, we go back to this simple example 1, right? And let's say we're going to reset the program because I'm going to rerun this one. So I'm going to do an optional stop. I'm going to stop just prior to the measuring cycle. Now I'm going to bring on my basic blocks, and I'm going to kind of single block down. So just bear with me a sec. We're going to get into the cycle. But you're going to see when the system physically gets in, and come on down. We like our stop reads. There you go. There's your mesh command. So this is the function that the cycle's calling to perform all of these tasks. When I'm making custom cycles, I try to use the cycles in conjunction with each other when I can. But if I can't, I'll go right to the mesh cycle and let this handle it. And let's finish her up. Now, when dealing with the cycles, probably the next question would be, well, if I want to grab that data, how do I know where it's being written to? Specifically, when I'm just using a measure only. So back to this program, this is the easiest way I find to find where the variables are being written to. I use the onboard help. So just open up the cycle, go to your help. Help is content sensitive, so it's going to open the help relative to that cycle. And if you scroll down to the very bottom, you're going to see a link to result parameters. This is all of the variables that are being written to during that cycle, during that measuring cycle. So this is the quickest way to find which one you want, or at least get in that neighborhood. Now, where are these OVR variables? So those are going to be found in the offset table under user variables, and those happen to be what we call channel GUDs. GUD stands for global user data. And these are just, oh, what's my password set to? Oh, I'm still running. Making a liar out of me. That's weird. I don't know why I'm not seeing it. My sinew train looks a little funny. It's an OVR. It's a quick search, but OVR. And I'm not sure why I'm not seeing it. I think my sinew train did a little something funky. Well, you'll have to take my word for it, but that's where you're looking. You're looking in the channel GUDs, and specifically for your OVR variable. No, it's not. Oh, is it a system channel? Oh, maybe I was in the wrong one. Let me just search. There it is. Now I don't feel like such a moron. Okay, so I needed to go to the appropriate variable section. So I want it to be under channel GUD, but I want to be selecting my system GUD variable. I had left it on one of the other ones. So there, I can do a search. This is the variables. Now, you don't necessarily have to get to this screen. If you want to see what they are, this is where they were last wrote, and I can check which ones are which. More importantly, though, I might want to set a variable to an R variable, right? R variables is just a quick little dumping ground for any users to use to write. These are what we call volatile variables. Now, if you want to learn a little bit more, check out my variable programming webinar. I go into a lot of this stuff in detail. But now you can start to do all kinds of crazy stuff. I can grab data, write an OVR to an R variable, and then do some math based on it, some trig, whatever I need to do, calculate an edge, calculate an orientation. You're going to do all that just using those OVRs. So again, the trick to find the variables, just go back to the cycle, open the cycle up, go to Help, and then scroll to the bottom. You're going to see the result parameters. This is also in the manuals if you want to search for it in the manuals, but I find it's much quicker and cleaner to find it here. And then certainly based on the cycle I'm in, I may have more or less variables to choose from. Okay, so hopefully the mesh cycle is starting to make a little more sense for you guys. It's a very handy, very powerful tool to start to fool around with here. Now, we're got a little more content to go through. So we're going to look at, okay, we're starting to use these things to write to offsets to drive things, but what if I want to just do some measuring? So we have the ability of kind of just capturing data, whether it's writing to the offsets or it's just doing a measure command by itself, and then displaying some different stuff. So one of the first things we can do is force a pop-up display in the auto screen to tell the operator what the measuring results were. Now there's a machine data, this measure result display data that would have to be adjusted, but you got a few strategies here as to how you want to be able to feed or pop things up on the control. And let's see if my video wants to behave itself and play. Of course not. Let me start up. There we go. So here I'm just running a simple cycle in auto. There's the measuring cycle like you saw before. And then with that parameter set, it'll do a pop-up, show me a bunch of values, differences. So it's just a nice, quick, clean way if you want to have measuring results pop up on the screen for operators to see and to adjust or at least determine. Now, if you're using the safety tolerance, we're automatically going to pop up that display if it's out of tolerance. And when we alarm out, we'll tell you we alarm out. This is more if you want to get acknowledgement during the measuring routine. And then how long it stays up for, it can stay up for 8 seconds. It can force the machine or program stop. So there's a bunch of little MDs here that you'd want to look at. All these machine data also are referenced in that measuring cycle manual, like I mentioned. Additionally, we can start to create reports. So in version 4.7, which is our current release version, actually we're out to 4.8 really, just last emo was released. But come 4.7, we now have the ability through a little cycle to auto-create reports. So what you can do is you can add this report logic to it, and now as it takes different measurements, whether it's writing an offset or just doing a measure only, it'll write a report for you. So looking at our machine back here, maybe I'm going to take our simple program example 1, but just prior to my cycle, I'm going to go back to the measuring commands, but I'm going to look for the button called measuring results. And this allows me to do a couple different things. I can tell it whether I want to display right here, right? So I can drive the display as long as I'm using this cycle. So here I'm going to display for 8 seconds. I can create a log file, a standard report or a user report. I can control the formatting of the file. We can do what's called appending or new. That means every time you run the program, do you want to add the new results to the bottom of the file, or do you want to overwrite the file? So if you're trying to get a history during the production run, you might want to append it. If you're just only curious or concerned about the last run, then you can do a new one. It'll rewrite it every time. And then you can tell it where you want to write it to. So you can write to a directory, you can write as a part program, and then what you want to call the name of the file. So here I'm going to call it Mesh Protocol 1. By saving this and inserting it prior to all your measuring, it's just a one-time deal to start it. Now, as I run the program, so we'll come back and run it real fast. And I don't need my ops stop on, so we'll take that off. I'm going to run the program to length. It popped up for my 8 seconds. It's quicker in Sinutrain, just because we speed up the clock time, so it doesn't seem like it takes as long to run. Real world on the machine would have stayed up for 8 seconds. And then we also now create, depending on where I told it to, I create a little report. So this is going to give me the data of where it measured, what it wrote to fine. And if I keep running it, since I amended it, all right, so we're running, does its measurement, does its next measurement, there's its validation. Since we have an amend, it's made the file a little larger. I open it up, scroll to the bottom, and now I've got a little bit bigger because it's adding to it each time. Again, set it the other way, it'll just overwrite. So this is a very handy and quick method of being able to start creating reports right there in the control, right from our cycles. Okay. Now, with that being said, if I'm maybe looking at programs that were methodized for older software or running a machine that's older, I can still do the write command, but I didn't have that nice little fancy cycle. So you use this command called write. And if you go to the job planning manual, it'll give you some detail on that. But this allows you to do manual writes, and you can direct that to a file and tell it what you want to write at any given point. So it's kind of like the equivalent of the MEAS cycle for the probing routines. This is the equivalent to that other cycle I just showed. In fact, this is what we're using in the back end to create that cycle. We're just doing a string of these write commands. So this is a handy cycle to know. Typically, if I see guys that have been doing this type of logic for a while, they get these giant files with all these write commands, because that's how they're capturing the data. Now, if you try to write to external memory, that gets a little tricky. Normally, you're just going to write to the NC and write a file there. You can do it. Don't let anybody tell you can't, but you do have to set up, and there's some specific pathing, and you have to use the xopen command if you want to use that. EXT, OPEN, I think it is, might be slightly abbreviated more. To get the right command to write to external memory. But as long as you're writing to internal memory like NC, you can then write to wherever you want. Okay, so from there, we have our formats like I just showed you. What's kind of neat, though, is we also have the ability of writing this stuff in JOG. Now, you do have to turn that on. It's under the settings function in JOG. So you expand your horizontal keys and turn on the settings. I can show you real quick. But you can actually now in 4.7 create logs as well from the data. So if you want to be able to capture what the operator is doing as far as from the setup side, every time he does a measurement, you can expand, go to settings, and you go to measuring report, and then you can turn this function on. You can tell it you want to do a measure report, new or append, where it's writing to, and it'll start to build this report, and then the name of the file. So that's pretty handy, and that's certainly new to version 4.7 functionality. Okay, we're winding it down. So the last feature, and we're not going to go into detail on this, but I did want to just kind of throw it out there to make you guys aware of it. Not only can we use our measuring cycles to come in and measure the part and write offsets or do the functionality we've been talking about, but we can also use it for alignment of the machine or safety or health checks of the machine. This becomes real important when you get to advanced technology 5-axis style machines. So with this being said, you use a cycle called 996. It's a kinematic measuring cycle, and that comes in and allows us to qualify or calibrate the machine based on a bunch of measurements off of a tooling ball like you see here. So that is another cycle. It's something that interests you. You can look at it in more detail. It is talked about in the Measuring Cycles Manual. Kinematic measuring, I believe, does require an additional license because it's part of a kinematic adjustment process. So it's a little bit more elaborate. But a lot of OEMs I'm finding are selling the machines automatically with this functionality so they can use it to adjust for any inaccuracies in the machine. Now, this does not alleviate the need for proper alignment of the machine when it first gets into your facility. This isn't going to mask a bad install. If the machine's not square, it's not trammed, the head's out of whack. So just keep that in mind. You know, a lot of guys try to use these types of cycles as the end-all be-all. That, oh, the machine's just going to adjust itself and it'll be perfect. No, the machine has to be square. It has to be straight. But this allows you that if any inaccuracy has changed over time, things have settled, things were crashed, it could possibly adjust for those. But if you're getting a new machine installed, you don't want to run a cycle like this. You can do a check, but get it installed, get it to the way it was sitting at the factory. It should run as good on your floor new as it ran at the factory. And then use this for health checks, or as the machine gets older, you can do adjustments in your kinematics to compensate for the machine. Okay, we covered a ton of material in a pretty short amount of time. I'm sure we got a bunch of questions. So why don't we take a little time and go through some of the questions. So if I scroll back here, and if you guys haven't got a chance to write them in, we see a bunch of here now, but please feel free to type them in as we're starting to go through them. Okay, so let me scroll up. So we did get a question from Gary. I use the Siemens control on a bloom grinder. Is the part programming part the same? So, you know, I'll have to apologize, Gary. I don't get the opportunity to get on very many grinders. The other tricky part with the grinders is a lot of those OEMs do custom front ends. Now, what I will say is the core cycles are the same. They are available there. Whether or not you can get to them from the interfaces easily, I'm not sure. That would be something we'd have to explore a little bit. What's nice about the 840 control, you can temporarily turn on the license if you want to try to see if they're going to pop up and what they're going to look like on your control. So really any of the licenses, if you go into the control, you're going to need to go to Machine and Setup, and you're going to expand your horizontal keys till you see the license button. Under All Licenses, when you scroll down, you're going to see a little checkbox come up, and there'll be checkboxes here. Now in Sinutrain, we license everything. On the machine, there's going to be a bunch of stuff that don't have checkboxes. Now, if you want to try a license, and for us, the measuring can be found if you do a quick search for measuring cycles right here. There's your P28. If on your machine you don't have it yet, there won't be any checkboxes here. Check the one box, and then you can activate what's called a trial license period, and you can test them out. So I would say that would probably be the first step. Would be let's try to turn on the license for the measuring cycles and see what they look like. But I'm expecting the core cycles will be there. Whether or not the front end has been changed, I don't know. I'm not quite sure I follow Rob's question. It says channel GUD greater than GUD select. If you can re-elaborate on that, I would appreciate it. Let's move on down the list. Keith says, how do I use the probe to select one of 4 programs? Measuring in Z, look for one of the Z heights and select the part program according to the measurement. Oh, okay. Usually what I would do there is I would have a main program, and I would have some simple logic statements set up. So I would come down, I would take my measurement, I would then do a if then or some type of logic statement, check out that variable webinar program I did. I get into some of those logic statements. But what you can do is create conditionals. So then when you drop down to the area in that main program, then it's just like calling up any other subprogram. So you're just going to then literally call the other program. And calling up subprograms in the Siemens control is pretty easy. If you are inside of a program, just go into any program, and it's time to, let's say right here, I want to call up a sub. A couple different ways to do it. You can go to various, go to subprograms, and you can literally search to whatever program you want to call up, and it will write the path for you. If your program's sitting in NC memory, you can just type the name of the file. So if it's xyz.mpf, just type xyz.mpf, and it'll automatically find the file. So there's a bunch of different ways, but that's how I would handle it. I'd have a bunch of logic statements, and then when I get jumped down to the appropriate logic statement based on my measurement result, I just call that as a sub. You can call any program from any other, so it's not really a subprogram. It's a main file. It can have all the tool changes and everything in it. We're just allow you to jump between them. Don't get caught up on the concept of subprograms. You can make subprograms in the Siemens control. You don't have to. You can call any file from any other file. It's very, very flexible as far as that's concerned. Okay. Dave, oh, Dave was just thanking. I guess he had to jump off. Well, thank you, Dave, for joining us. So Dave is saying it's a custom front end. Dave, let's still try, like I mentioned, the license option. I don't know where they would have hit it. I don't know how they would have gotten to it, but let's see if we can at least activate the cycles. The other thing, you can always discreetly write the cycles if they didn't give you the graphics for the easy screens, like you see, or you know, what we call data masks. That little conversational window pops up. Nobody says you can't write the cycle longhand. In fact, that's how CAD/CAM guys do it, right? They don't have a graphic. So you could literally write cycle 978 if you need to, but first we got to get the license on. All right. Rob, that was just me trying. Oh, help me find the OVRs. Thank you, Rob. I appreciate that. Okay. And we have, when will you do a similar measurement presentation with a shop mill? I can probably schedule one up. You know, my next two are scheduled out, but probably sometime this spring we could certainly do another one of these, but you know, concentration more on the shop mill side. Maybe we can add a little more logic in that one too. All right, another question. Let me just open these up. I got a bunch of questions here. We always hide the questions on me. Give me a second. Okay. From the CAM perspective, I get asked a lot about measuring a bore or a boss or aligning a fixture offset to the center of that feature. Can you discuss if that is possible and how the G-code would look? So that was probably written before I showed the measure command, or even just using some of the primitive commands. But keep in mind, if you're going to start to daisy chain multiple cycles together, that's where you're going to want to use the OVR variables. Grab the data and write that. But you can use any of our cycles in conjunction with any of the other ones. So normally what I do there is measure a feature, grab the OVR, because a lot of times the next cycle will write over that OVR. So grab it, save it to an R variable, go measure something else, save it to an R variable, then make my calculation. Is DZ always a positive value? Yes, because it's an unsigned value towards an incremental value. So you don't have to associate any sign. In fact, if you give it a sign, it will error out. Additionally, are there any R variables or R values we cannot or should not use? Okay, so that's a good question, Tim. So R variables are what we call volatile variables. So the sheer nature of that is you're allowed to write to them, but anybody else can write to them. So generally, I would say if you're going to write to an R variable, there's none that I would say are reserved. What's going to be reserved is, you know, the global user variables. You know, if maybe you put Renishaw cycles in it and they create a bunch of custom user variables, that'll be all under those global user variable sections. The R variables, let's say write to any of them you want, but don't expect the value to be there, especially after the program has been cycled. because you never know what's going to potentially use an R variable. So I would say during the length of the program, if you want to dump to an R variable and then grab it and do something with it, by all means. But I wouldn't write to an R variable if you're expecting to then get to that variable, I don't know, 3 jobs later, let's say. Then I would create my own custom GUD table, referencing back, not to keep plugging my previous webinar, but referencing back to my variable programming. I did show you how to create custom GUD variables. That's what I would do in that case. But if it's something like we did now, write a quick value, do a little math, bring it in, yeah, any of the variables are open and play. And if any other cycle developers were writing to the R variables and not realizing they're volatile, well, shame on them. But they certainly shouldn't be. Okay, David. Oh, what is the link for the webinars about usage of the variables or my variable part programming? So if you go back to the CNC4U website, I gave you the web address on. Let me bring it back up again here. Pop it back up. Oops. All right. I'm going to get right back to the top. I want everybody to grab this. But if you go to, come on. There we go. Go to CNC4U or go straight to my CNC-webinars. In the webinar tab, there's going to be an archive. I believe that one's sitting under milling. If you scroll down 3 or 4 webinars, you're going to see variable-based programming, and that's where you can get to the link right from that page. And always check this main website. This is a great spot for you guys to keep looking for webinars I did. If you want to refer them to colleagues or customers, by all means, they're all there. What types of probes are supported? So if you recall back here, in the beginning, I showed you quickly building a probe. So these are the probes. This is Dave's question. These are the probes that we support. So a straight 3D probe, the Type 710, that's a probe that can measure in all 3 axes, typical Renishaw, Marpos, Bloom. We have monoprobes. Those are probes that can only take measurements in a couple directions. We see these a lot more in like lathes and stuff like that. We have L probes. So that would be a probe that's hooked. So if I need to measure up underneath a feature. Then you have star probes that can do the same, but now you have 4 points. So these would be the typical probe orientations that we support. Okay. Dave meant brand, Renishaw, or Marpos. So the cycles are not brand specific, because what ends up happening is a switch is a switch, right? We've got a dedicated input. So it really doesn't matter whose part probe you have. All of our cycles will support anybody's part probe. The only time we get into a case where we have trouble with our standard cycle supporting it is lasers. So lasers is a different beast. When you get to lasers, and that's for tool presetting, there's all sorts of different types of focal points, type of laser designs. So the cycles that run those lasers are very specialized. So then you are going to need to use the manufacturer's cycle for laser. But when it comes to touch probe for tool probes, or when it comes to part probes like we've talked about over the last hour and a half, you can use anybody's part probe. Doesn't matter. You're just going to go through our calibration routine, and that's the trick. Now, I will warn you, if you happen to have, let's say you got Renishaw or Marpos, and they installed their cycles in the control, you're going to have to calibrate the probe twice. I can't seem to get any of these probing manufacturers from their custom cycles to write to the same variables we write to during calibration. So what will happen is they have their own calibration cycle. If you calibrate it, like I talked about here on that page, if you calibrate it with our cycle, our routines, that'll let all our cycles work. But the Renishaw cycles or the Marpos cycles won't work. So if you calibrate with the Renishaw cycle or the Renishaw routine, all their cycles will work, but our cycles won't work. So unfortunately, if you want to jump between our cycles and then a probe manufacturer's cycles, I would say, well, you're going to have to calibrate the probe twice. Honestly, how robust our cycles are and how well purpose-built they were for our control, you're hard-pressed to find somebody's third-party cycles that are going to outperform ours. So I wouldn't personally, and 90% of my customers that are using this are using our standard cycles. I'd say usually if I see somebody running like Renishaw or Marpost, it's maybe because they're posting them from a CAM system, and then they want to use like the Inspection Plus functionality, and that's fine, that's great. But you got to calibrate the probe through their calibration cycle. Cody has a Miltap 700 with a Renishaw probe. Great machine. I've run many in my day. We have new machines coming with Bloom. Will we need to rewrite our current code for this change? Again, no. As long as you're using our cycles, it's all the same. It's universal. It doesn't matter which physical probe manufacturer you were using. And then our last question here. I'm very interested also in shop mill, and for now, I will give it a shot. Show today, yeah. So the question back to the shop mill, you're going to find it's extremely similar to what I just showed you. Very similar. So really just, you know, try to apply it. I'm sure you're going to pick it up and kind of run with it. Okay. What else do we have? A couple more questions rolled in while I was talking. Got that. Okay, so Rob asks, is there a way to get machine coordinates from probing results from within rotated coordinate systems? So that goes directly back to the example I showed where we're using cycle 800. So again, as long as you're using our dynamic fixture offset, which is really our 3+2 routine, our cycle 800 routine, then you can probe in any orientation, and it's going to take that that rotation, that dynamic rotation into account, a coordinate rotation, and give you the right result. So I think that's what Rob is referring to. If it's not, or if I missed any other questions here, because we got a bunch of them. Oh, can you go over a line plane? This is from Matt, using 3 points to put a value in G54? Sure, absolutely. So let us go back to the simulator. So what Matt is referring to is back here in, jog, and we can do it certainly in auto mode. We have a function called align plane. Now what align plane does is allows me to pick 3 random points and then align the machine to those 3 points. So it's creating a plane, and then it's aligning to the plane. So what you're going to do, and I'm going to maybe write to a different work offset, one that I haven't been playing with. So I'll go to 520, let's say. Is you're going to jog the machine to some random location. So right now I'm going to bring my Z down a little bit. I'm sitting at X0, Y0. I'm just going to be somewhere on the part. And it really doesn't matter which 3 points you pick. Then you're going to initiate a cycle start because you've got a probe in the spindle. She's going to come down and take a measurement. And it's going to show you that P1 saved. Now, you're going to manually jog the machine to a new location. Again, it doesn't matter where I'm going. I need to, in this case, change my Z a little bit because I want it to show a measurement. I'm going to initiate cycle start. It's going to come down, in this case, measuring in Z, trigger that top point. And now I'm going to move to some other location. Maybe I'll go down a little bit, whatever. Cycle start. So you're just going to take these 3 measurements, and you're going to get the 3 blue highlighted fields are going to pop up. Then you're going to say set work coordinate. You got to remember to hit this button. If you forget, you're going to lose the values, and it's going to write to G520. So set work coordinate. Do I want to activate? Sure, we'll activate now. Do I want to move the probe perpendicular? No, I don't want to move anything. So you notice 520 gets loaded, and now I'm showing that I have some kind of rotation happening. So what it did, just like the align edge we were looking at, is in my work offset under 520, right there. I go to details, I see it calculated 2 adjustments. And this always writes to the coordinate rotation, right? So it said, hey, based on those 3 points and the plane I just created, it means that to make the spindle normal to that surface, I would need to rotate about my X 19.4 and about my Y 2. And these can be plus or minus values. It all depends on the 3 random locations. So she now knows a surface. So if I want to then send my 5-axis machine normal to that surface, I then drive the machine to that position using the swivel cycle. So a quick swivel cycle telling the machine to go to 0, 0, 0. I'm going to do a little retract action in my Z. Will initiate these two planes, and the machine will then calculate automatically for you where it would need to spin the B and the C to make that normal. So now I should be perpendicular to that surface. Now, if I'm on a machine that doesn't have rotary axes, it would set me a plane skewed. So if I jogged it, I could jog relative plane, but obviously I can't tip the spindle. I'd have to do that manually if I could. Now, the same cycle then applies in the programming environment. And it's going to work the same way. You're just going to have to position it to those 3 points in the cycle. But if you go to 3D, align plane, so here I pre-position to a location, and then I'm just going to use these values to move the machine around to really capture 3 points. It's going to do the same thing like you just saw. It's going to create that plane. So hopefully that was helpful for you, Matt. Okay, I think I got everybody. If I didn't, by all means, please feel free to reach out to me. I'll put my contact information one more time up on the screen. Right here. Shoot me an email. If you'd like a copy of the slide deck, I'm more than happy to share it as well. So just let me know. I can give you part programs if you want, any of this stuff. So thanks everybody for joining me. We had a great crew today, a lot of great questions. I appreciate it, and check out the next one. I'll see you guys in about 6 weeks. All right, everybody take it easy.